Test, test, test. Can you hear me? Can you hear me? Never know. Test, 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 test. Test, 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 test. Okay, okay. Huh. Set. GPT. Test, test, test. Okay. All right, let's start. This is not very loud, is it? How about now? Test, test. This fine? Uh, Guys, everyone, please. There's something. Yeah. I had uploaded them yesterday, but there was another publish I needed to press. They're online now on Canvas. So apologies for that. Apparently, you need to publish twice. But yeah, you can look at them online in Canvas, and I'll make sure to have them one day ahead. All right, let's get started. Welcome to the third lecture of Deep Learning 1. We'll be talking about optimizations today. To put this sort of in the broader context, this is roughly what happens when you optimize neural networks. So first of all, of course, you need to have a model, where you can choose the architecture and the weights, how you initialize these weights. Then you compute some sort of loss, for which you then use, of course, augmentations or regularization. They all go into this computation of the loss. And of course, how we do backprop. That's pretty much what we had the last time. And what kind of loss functions exist, we also discussed very briefly. And you remember that from ML1. And today we're going to talk about these three topics. How to initialize weights, how we can keep improving these weights using gradient descent, and upgrades upon gradient descent, essentially. All right, so let's get started. These are our three main topics. So first of all, let's talk about optimization versus learning. So generally optimization, you might recall from some basic mathematics lectures. The idea is that you have some sort of parametric definition of a model, which model is very broad. It could literally be a linear function, for example, and you want to find which kind of parameters that you can choose optimize this model. So you want to find these parameters that optimizes a certain, and these are called objective functions, cost functions, and usually in the process of learning, we call them loss functions. But generally, these could be very broad. So you could even be talking about, for example, finding the optimal flight schedule, given some resources and population. Some of you might know this. It's like optimal transport problems, for example, and have been, it's basically a whole branch of mathematics. Learning, on the other hand, is all about having two kinds of data. You have the observed data and the unobserved data. And our goal is to learn, to optimize something on the learned data and apply it to the unobserved data. And basically, in this process, be able to generalize. So generalize in this case means we assume that the training and test data come from the same origin. So it's not like you're training on, let's say, cats and dogs, and you're testing on different car models. So that is not quite what we mean by generalization, but they will be different data. And that's what we mean with learning. We want to learn something that generalizes to unseen data instead of cramming for the exam. So we don't want a model that learns everything by heart, just like we don't really want students that learn just whatever is on the slides, but actually understand and generalize to new problems. you can also think of it this way, right? Like, for example, the right plot, and we'll use this plot in many kinds of contexts, but in this one in particular, actually the right one really hits every point, right? So if this is your training data set, the right one really has the lowest loss possible. But now if you think about, okay, let's pick another x2 and you want to predict which x1 you have, probably the left model is much more generalizable. So this is all about learning by heart versus having a model that actually generalizes. All right, so typically this is done using risk minimization. So you want to optimize on the observed data, a typical loss function. This could be looking like this. So we minimize over the weights W. And do the expectation over our data, which is X as inputs, Y as labels, for example. We have a loss function which depends on these two things. So F in this case could be a neural network or is a neural network. And then we have this second term, omega of W, which we'll actually go into only in the next lecture itself. But generally speaking, here we have, again, this sort of modular structure of a neural network. And in simple words, the first part, make sure that the model predictions are actually good. And the second one will be that it's not too geared towards observed data. This is exactly what can, for example, differentiate the left model we saw from the right model. Now, what we're writing here is P data, where usually P data is a real underlying distribution. So in the case of statistics, you can really write this out, what P data is. In the case of the real world, we don't know what this real world distribution is. So this real distribution isn't quite available. So we usually have to make do with an approximation. This approximation is, in practice, the training data set, as I mentioned. So it would look like this. Pretty much everything is the same, except that now we have this p hat data as an approximation given by the training examples. And now we're minimizing the empirical risk because that's what we will see. And we'll get back to this omega term at a later stage. Now we want to minimize this function, and we already had this last time, right? So we do this d by dw, that's literally the gradient. And how we can compute this across a large network is with the backprop algorithm. But now, given that this delta, that we've computed this delta, which could be the step that we want to go in, we still have some possibilities where to go. So delta, the gradient, points in the direction of the steepest descent, so we know that, but there's much more to this. Generally speaking, this procedure is called gradient descent. As you recall, the general formula of gradient descent is as follows. So you update the weights. So weights given at time step t plus 1 is your last weights, wt, minus eta, which is a step size, the gradient. So in this case, the gradient of the loss function with regards to the weights. If you compute this this gradient from the whole data set, typically this is referred to as gradient descent. If you compute this from a mini batch of samples, and we'll go into that one a bit more detailed later, it's called mini batch gradient descent. A batch is just a sample set which isn't the whole data set. If you compute this from just a single data sample, so think of a single image and a label, or think of a single sentence and, for example, the associated sentiment, this is called stochastic online gradient descent. Now, if you read most papers, people aren't too careful about this, and people typically just call this one stochastic gradient descent, because this one is, in the end, the only one out of these three options that works. And so people typically just refer to this as stochastic gradient descent. And of course, stochastic gradient descent sitting in between 1 and n equals data size, being somewhere in between, has this parameter of how large this mini batch size indeed is. And of course, keep in mind that we have non-convex landscapes, so it's not a given at all that we can find the global optimum. In fact, this is a screenshot of how these kind of loss functions can look like for neural networks. Sorry, yeah? Yeah. Mm-hmm. um, we can we'll be very detailed. So if we mean, unless we talk about the coding part, because it literally for torch it says torch SGD, and then it will be that. Otherwise, we will say mini batch stochastic gradient descent or online gradient descent, or maybe we can even add full data set gradient descent just to be sure what is being meant. Good point. These are how loss functions look like. So they're not very smooth at all. And you can easily think oh yeah, what we're visualizing here sort of is that in the y-axis you have the loss function value, and that's why it's sort of a surface. And on the x and y axis, you have, for example, different parameters. So if you go slightly towards the right, say you're changing one parameter slightly, you're increasing it slightly. And this has, of course, an effect on the overall loss function. And these loss landscapes are extremely expensive to compute because essentially for every point here, you're computing, for every point in this giant grid, you're computing the loss function and then plotting it in a 3D manner. And actually, this is pretty interesting to explore. So we're gonna do this here quickly. Let's see. All right. Let's see how fast it is. Okay. So this is, for example, a real loss landscape from a neural network. You can visit this later on as well. So, for example, this one is, I think, somewhere it says it's some sort of vision neural network. Oh, it says on the description, yeah. Convolutional neural network trained on this small data set, and you can explore how, for example, different optimizers work on this. So you can, for example, start optimization from this place. Sorry, let's do it from here. And for example, it gets stuck. This one also gets stuck. It's extremely difficult just with gradient descent to find this good place. So somewhere here you can add more optimization parameters. This is not great, but this is actually the thing. So what we'll be doing in this course is basically checking out this parameter, which is momentum, that will help us actually find this value of the optimization function. So no matter where you start, you'll actually not get stuck and actually go to the optimum. Yeah? Oh, it's the learning rate actually. Well, even if you use a lot of starting points, you can see that depending on how you do the optimization, they might not end up working well. So, and then if you I mean, also this is 2D, right? Like the neural networks have, let's say, between 5 and 50 million parameters. So it's extremely difficult. So even strategies like evolutionary search and so on simply do not scale very well for neural networks. Sorry? Yeah, we will go to that in this lecture today. Was there, yeah? Yeah, so you can actually explore that, how this is visualized. The learning rate is not a parameter, right? The learning rate is a hyperparameter. But you're right, like this network, even this being a convolutional network, has many parameters, and you're not just visualizing, as far as I remember, you're not visualizing two neurons here, but instead you're doing some sort of, you try to find the directions, the two main directions of linear combinations of neurons, which give you the most change. And so you can visualize this as basically moving in this neural network space. Yeah. I mean, you can make up all kinds of examples where they fail. For example, and we can, for example, in the example where we'll talk about convolutional neural networks, they are one particular structure that we put into the neural network architecture. Technically, nothing is stopping from a fully connected neural network to going to this structure because it's very efficient and because it solves a lot of problems. Yet, if you have a giant network with just fully connected layers and you throw it at an image dataset, despite the fact that it's going to be very computationally costly, it will just be such a difficult optimization problem. It will never find this very good solution that is generalizable. So if you encounter stuff that's not easy to optimize, you will need to change your neural network architecture, maybe your loss function, yeah, all kinds of things really. But you definitely do encounter these sort of things where you just cannot seem to get the loss to drop. Loss is the one thing you want to optimize for. So what people typically do in practice is to see whether their model is capable of learning anything, they would take one batch and just iterate on this batch. Instead of taking the whole data set, they learn something on this batch and see, okay, can they at least minimize the loss on this single batch? And that's usually a good trick. But there's no, like if you give me a network and a loss function, like there's no procedure that can tell you whether this will be able to train or this won't be able to train. It's a bit yeah, there's no known way, unless the problem is of course very easy in the case of parabolas or in the case of linear functions, because here we know. All right, and here's actually the difference in a bit more visualized way. So in this case, the visualization on the right-hand side is actually stochastic gradient descent, which could be visualized here for each batch, or it could have been for a single sample. It doesn't really matter, but the main thing is the same. Gradient descent, the classic whole dataset gradient descent, doesn't zigzag around because it literally computes all the gradients and averages them, while stochastic gradient descent always picks new samples. And we'll take a look into how stochastic gradient descent works in a minute. SGD, stochastic gradient descent. So as I said, it takes a couple of samples and then computes the gradient, and as such it approximates the whole gradient of the whole data set by just sampling a mini batch. Gradient descent can actually also get stuck easily, and so this stochasticity that comes from sampling a mini batch is actually quite useful. And how much variance we have when we use stochastic gradient descent is given by the standard error, which is given by the variance divided by square root of n. And square root of n is how many samples we take to compute the gradient. And you can see that this is simply as the square root of n. So if you want to get twice more accurate gradients, you need 4 times more data points. This simply comes from statistics. And also the batch size NB is very dependent on the task you're doing. For example, on videos and large images, this could be 8. For self-supervised learning and other tasks, this could be 4,000, for example. And for language NLP models, this is even larger, up to 16,000. A quick question here. So we said that for videos we use a batch size of 8 and images maybe 4K. So the question is like, why? I think you have enough, you know enough that you can answer this. So is it because the high correlation between frames requires lower batch sizes? As you know, videos have a frame rate of 30, so that's like 30 images per second. Or second, the GPU cannot handle much more. Or number 3, videos are processed at higher resolution than images. So have a think. All right, 1, 2, 3. So lots of ones, a bit of 2, lots of ones. All right. It is number 2. So regarding, let's start at the end, video, regarding number 3, so yeah, videos typically nowadays are 4K or whatever on YouTube, but in deep learning, we still process them typically at like 224 by 224, which is as small as we treat images as well, so that's not the main reason. The high correlation between frames requires lower batch sizes. It allows us to use less frames per video, but that because that's no reason to use a lower batch size. Like the main reason is that GPUs cannot handle much more, because a batch size of 8 for videos, if a video, for example, has 30 frames, that's 8 times 30, that's already quite a lot. So typically, and batch size here means items, right? Each video could be having 30 or 60 frames. That's why the GPUs cannot really handle much more. And depending on the settings exactly, you could maybe fit a bit more. Another aspect which I didn't write here is actually that video models are also more expensive, because now the input isn't just 224 by RGB, but it's 224 by RGB by the number of frames you're processing. So this could be 30, right? So the input is much bigger. So these architectures are also much heavier to compute. Any question? Yeah? Yeah. Generally, yes, we'll get to that point actually in the next few slides. Yeah, so we have this point, which is already going a bit in that direction, that randomness actually helps because it gets less stuck. And of course, you have more randomness if you have smaller batch sizes. Important note here is that you always take a new mini batch every time you go through the data set. So one epoch, as you recall, is going through through the data set completely. And every time you've done that, you reshuffle the data set, so you never pick the same mini batch twice, at least on average. Make sure you actually shuffle it. And if your data set is really imbalanced, you might want to balance it or rebalance it in a way that it is balanced such that it trains better. And this shuffling you can actually try yourself. So either in this assignment or in the next assignment, this is like something really funny, easy to do. In the train loader, just make the shuffle equals false, for example, and see that this has a big impact on whether your model actually trains to a satisfying performance or not. Right, about the batch size now. So a large batch size gives you a more accurate estimate of the gradient. But as we saw with the standard error, it has less than linear returns in terms of how good it approximated. The extremely small batch size underutilizes the hardware. Also why? The important point is that if we do any sort of forward pass, we can reuse the computations, right? They're all matrix multiply, and for every item in the batch, the same operation is being done. And like loading an operation into the GPU memory and then doing it is more efficient than doing the same. So doing a forward pass with a batch size of 10 is much quicker than doing 10 forward passes with a batch size of 1. Quick note that typically people use batch sizes that are to the power of 2. But yeah, the small batches can have this regularizing effect because they can add noise to the learning process. 1 second. They typically require a smaller learning rate though, because they're less accurate. So if you go a step too far with a probably very noisy gradient, you might end up in a bad place. And this general rule that is very important if you're coding stuff is you should make them approximately proportional. So if you're doubling your batch size, you'll double the learning rate. This doesn't have any real mathematical background, but has been like there's some better ways to scale, but this is still a fairly standard way. And with that, people have done, for example, training of ImageNet in a single hour with a batch size of 8,000. And this is also the reason why people don't use very small batch sizes, is that typically you want to be utilizing your GPU, so you use whatever batch size fits on the GPU. Yes. I think, sorry, first in the back, yeah. That's about the standard error we had. You know, the standard error of how good we are approximating the real gradient is sigma divided by square root of n. And square root of n is less than linear. Yes. Yeah, yeah, we're using them synonymously. Yeah. No, that's a good point. Yeah, this one is actually has a proper reason. It is because the GPU internal structures are configured that way. So for example, and you can actually see similar things in NumPy arrays. If you, for example, make a list longer, it will always double in size at powers of 2. So this, yeah, I think pretty much everyone has implemented that, but at the same time, at the moment, at least, there's almost no alternative to GPUs from NVIDIA. So there's more competitors coming to the market and other kinds of soft hardware, but at the moment, it's NVIDIA. Yeah, yeah. Yes, you do it with a batch size that doesn't, where your model doesn't complain, where it basically manages a forward pass and ideally a backward pass as well. So you do it in the normal inference mode. And let's say this was a batch size of 64, and this took you 3,000 megabytes of memory, and your GPU has 9,000. So you can double it. So you can multiply it by 3. So that's how you do it. Yeah, just doing that. You can actually compute it, like numerically, how much it would take. Yeah, but why would you? Um, all right, so let's see. Yeah, so as I said, SGD is really the key algorithm how we're optimizing stuff. The reduced sample size, even though it introduces noise, or because it introduces noise, doesn't make our optimization less good. And another reason why this is the case is also that the training samples might have lots of noise and outliers themselves, right? So sometimes if you select a random mini batch, they might actually not have this noisy sample, while if you always take the whole data set, you will always have this noisy sample, for example. And also, uh, it might be possible to get, if you're on your whole data set, you might get trapped easily in a local minimum. But if you always pick random gradients because of the noise, you won't get stuck. So you can easily think of two examples which are noisy in two opposing ways, and they will always cancel each other out. So you will always get stuck in some local, like saddle point. We'll get to saddle points in a minute. While if you take random gradients, you will less likely end up in such a local minimum. Now, stochastic gradient descent, as you know, it looks like follows. So we have our weight space here, for example. You have a weight vector w of t at time step t, and on the right hand side we have the loss function. So our model predicts well, first we sample a mini batch, then we get some outputs of our model. In this case, y is our output and y star is what it should be. So the loss is given by the distance to the diagonal. Just a simple regression problem. So we have selected 3 samples, computed our loss, and now we compute the gradient and we update it. And we do this rinse and repeat. Here's a table of pretty much the stuff that I've said so far. Generally, yeah, you can see that there's a bunch of differences and why you want to use stochastic gradient. However, this point about hyperparameters, more hyperparameters like batch size, is of course something to note here. Yeah, in practice, almost everyone anytime uses stochastic gradient descent, and sometimes we use, or often Very often there's other optimizers that are based on stochastic gradient, like Adam, for example, and we'll go into these in the later part of this lecture. All right, another summary here. What we did is first we define our neural network. As a combination of modules, we will try to find an optimal neural network that optimizes a loss function based on the empirical data we're seeing. In this case, argmin is not, of course, exactly accurate. As we know, we cannot find the optimal W, but only some local optimum or something that's close to the global optimum, but finding the real global optimum, we can never be sure because these methods are iterative. They won't tell you, hey, I'm done with optimizing. That's simply not possible for non-convex methods. And we rely on stochastic gradient descent methods, which have the following form. All right, so we can we can play around with another tool now, which is called Playground from TensorFlow. How many of you have seen this one already? All right, so quarter, half. So I'll be fairly brief. This is pretty interesting. So you can do the optimization here, basically. You have a learning rate, you have a regularization, which we'll get to. The main goal is to classify these from these. So it's a binary classification problem, and you can start the optimization procedure by pressing play. And now you can, for example, subtract neurons, or you can add neurons and see how the method learns this. You can see how positive or negative the weight is. Blue is positive, orange is negative. You can add a linear layer. So these are just plain MLPs. You can even have one here, which obviously then the input data is simply 1D, so it cannot do much. You can do all kinds of things. You can even vary the batch size. You can add some noise to the data. So this is really good to give you an intuition of what's happening in the optimization, and it's actually quite fun to play with as well as also the regularization, which we'll get to next time. You can see, for example, if you put it too high, all the weights will be 0, etc. All right. So yeah, play around with it. Gives you a bit of an intuition. There's some fun things to do. All right, so I've been already casually mentioning that neural network training is non-convex. So functions can be looking like this. And if we're in the non-convex context, we have all these problems. What learning rate should we use? What if the loss surface changes locally? And how should we keep going steps by steps in this highly nonlinear landscape? How can we avoid getting stuck, etc.? But first of all, just as a brief reminder, what do we mean by non-convex? So convex is defined by this function, literally from Wikipedia. And basically what it means is if you can have a string that connects any 2 points and it stays above the surface, then it's convex. You can also flip the function, and if you can then do it, then it's fine, then it's still convex, then it just means the negative of the function is convex. And now we consider, for example, this function, x1 times x2, like a really simple function that you will get with any kind of neural network. And you can already see why this isn't convex anymore. So yeah, if you go from this parabola from left to right, this looks exactly like on the left-hand side, right? So this part is convex, but as soon as you head down these alleys, down the saddle basically, the string starts crossing the curve. So it starts being, in this direction, it's not convex anymore. So put together, this function is not convex already. So, and this is the simplest possible function you can think of that's already non-convex. And for convex functions, there's all kinds of amazing solvers, which we're not getting into here, but it would be very easy basically. And we're not in this case. So that's why we have to deal with all of these iterative solvers. All right, so let's talk about the challenges in optimization. There's 5 main challenges. The first one is ill conditioning, which will bring us that a strong gradient won't be even good enough to optimize a function. So even if you have a good gradient, we'll go into each one of these in detail. The second one is local optimization, has these many local minima. Last one are third one are plateaus, cliffs, and curvatures. Fourth one is vanishing and exploding gradients, which I'm sure everyone will experience at some point during the deep learning journey as well. And fifth one is long-term dependency. So let's start with the first one, ill conditioning. All right. And now actually comes the slide with the Hessian matrix from last time. The Hessian matrix is a square matrix, which is basically the Jacobian of the Jacobian. So it gives you the second order derivatives, partial derivatives of a scalar valued function. We can call it f. In this case, it's f. It could be, in our case, it's always the loss function. And it basically describes the local curvature. And it describes the local one. Well, in this form, it's just a function, right? So it describes how the local curvature is at any point. But if you evaluate the Hessian at a point, it describes how the curvature is at any given point. And the Jacobian, much like its equivalent of the second derivative in the 1D case, describes how the first derivative is changing. So you can see in the middle picture, it has a negative first derivative, right? The slope is going down, but the first derivative stays like that. So the second derivative is zero, hence no curvature. On the left-hand side, you can see that the slope is getting steeper as we go to the right, and so the slope is changing. So and then the slope is changing in a negative way, so you have a negative curvature here. So this is pretty much the same thing that is in this 1D example you have in multiple dimensions, except, of course, everything is more complicated. And already, once we go to 2D, we can visualize a couple of these complications. The one point that I've already mentioned casually, which you have when you have x1 times x2, is the saddle point property. And you can actually quantify what kind of local minima you have if the first derivative is zero, and you can see in all of these plots the first derivative is zero at this location 0, 0. You can see there's all the tangential lines at these points do not have any slope with regards to x and y. With a saddle point, we have a problem, right? Because if this function is now the loss function, both of these gradients in this direction and the other direction are zero, but we're not at the optimum yet. The optimum is clearly somewhere if we go down the saddle. So this is problematic. We can quantify how ill-conditioned a particular problem is by having the Hessian matrix. We can namely compute the condition number, which is given by dividing the maximum eigenvalue with the minimum eigenvalue. And this measures how much the second derivatives differ from each other. And they tell us how much they are different, and we can visualize this somewhat with the following example. For example, here, if we're at the bottom of this mountain, we know the gradient towards the top at this point is very steep, while the gradient towards going to the right is not very big, right? So if you take the first step, the first gradient will be mostly pointing upwards, and in which case you end up at the top, and then you look for the steepest gradient, and then you'll be going to the right. Now this is fine for a mountain, which is just 2D in this case, but for an n-dimensional problem, this would require n steps. And furthermore, here it's even easier because you know where to stop. Like, you're not going to go beyond the peak of the mountain because we can see where we are. But in a neural network, we cannot evaluate the loss function at every step of the way. So it's even more complicated than that. So it's very important to pick a good step size because we cannot see where to stop. And we can, we'll visualize it in a second bit. We can compute how bad this ill conditioning is actually by doing a Taylor expansion around the point that we're currently at, which we denote by W dash. So you can check this is just the regular Taylor expansion you do around the point at W dash. And now we do a slight perturbation around this point by, for example, minus epsilon g, approximating one step in the direction of g. And then we can see that if this equality, if g transpose h times g is larger than g transpose g, in this case, the second derivative will have a detrimental impact. And so the loss can even go higher, even though we're taking a gradient step towards the direction where the gradient should be going down. So ill conditioning can lead to the point that actually we go up the gradient and have a higher loss function than before. And yeah, in neural networks, this means we have plenty of, or almost only saddle points and plenty of flat areas which do not have gradients. Second difficulty is the local minima. So we have, of course, local minima related to model identifiability, which is fairly easy. This just means you can swap around neurons in a neural network, right? So it doesn't matter whether you learn one neuron picks the role of another, as long as they together achieve the same role, you can swap around these. And this means your model isn't identifiable in the mathematical sense, but these aren't very problematic. So they are equivalent in terms of cost function value, they are fine. The local minima that we have in the next slides, they are the ones we need to be careful about, and they are the ones which make the optimization difficult. We need to keep in mind now that these visualizations, unless you do this thing that we have in the loss landscape explorer, you cannot quite do this. You cannot compute the loss value at every point of the way, right? We're practically blind what the loss landscape really looks like. So we're basically in this scenario, we're blind. We have a local measuring stick. We can put this on the ground and see where we're going. I mean, let's say this guy is trying to find the highest peak in this area. Or, yeah, the lowest part, let's say. And then he would go here, and then he would see the gradient there, and he would get stuck, for example, here. Even though, let's say, further towards the right would be an even lower value there where he wanted to go. But of course, he cannot see that, right? So that's what we mean by blindness. So it's easy to get stuck in these small values just because the gradient we're computing is always at this particular location. So this is really the tricky point. And momentum, as I've sort of hinted, will be the solution against that. Ravines is another set of is another description of what problematic things can happen when you try to optimize. It is the case when the gradients are large in one direction but extremely small in another. And again, because you cannot see exactly where you're going, for example, in the right-hand side, you might just go towards the middle of the valley, one step, and then go down the valley in another step, right? So technically you would only need 2 steps, but because you cannot see which way, you cannot see this value, you will always take slightly 2 big steps and you end up outside of the valley and you take the gradient and it points in that direction, so you keep going zigzag if you have these kinds of lost landscapes. The third difficulties are the plateaus and flat areas. Flat areas are tricky because flat areas means you have almost no gradients. No gradients means no updates, means no learning. So your function, your neural network will get stuck at the current set of values. That being said, flat minima, so if your network already has a low loss function and it is in a place where the loss function doesn't change anymore and it's and that place is flat, that is the place where it generalizes quite well to unseen data, actually. So now have a think why these flat minima might generalize better. Is it because they generally have lower loss values? Is it because neural network weights are always of finite precision anyways? Or because training distribution might be slightly different to the testing distribution? 3, 2, 1. right? Mostly threes and twos, and the rest are hedging their bets by not putting anything up. Um, One is not true, which I think most people got. I mean, at least generally speaking, there might be sub problems where this might be the case. Number two is also not the case. There's, of course, the point, which is quite interesting, that we're looking at parameter perturbations, and every neural network that we have is only of finite precision. So it only has a limited number of commas basically after the thing. So it's never perfectly a value. So that in that case fits. But actually, now it's good that I didn't provide the slides before, so otherwise you could have peeked, but most of you got it right anyways. One reason why flat minima are preferred is the following illustration. So your training distribution, as I mentioned, might look one way, your testing distribution might look slightly different. And so if you pick a set of parameters which has a flat minimum, it might generalize better to the testing distribution because it's simply, even if you get it slightly wrong, it might still be good enough. And actually in this paper, they show that small batch methods actually converge to flat minimizers. So that's why small batch methods are often preferred, at least. Now, so there's this definite trade-off with compute time and small batch sizes, though. All right, let's do, yeah, let's actually take a break now. It's been 45 minutes, so all right. All right, let's get started again. Yeah. All right, moving on. The fourth difficulty in optimization. Um, oh yeah, no, we had this is another slide for the fourth one. Combining flat areas with very steep minima. Right, I'll wait for a bit. If you could take a seat, please. So what is extremely difficult is if we now have flat areas with very steep minima, because the flat areas won't give us much gradients, and the steep areas are very difficult to find. Um, so actually, this is an easy example that you can actually play around with yourself. So imagine you're doing classification with cross entropy, and now instead of plugging your usual outputs that you get from a fully connected layer into the softmax, you multiply these values before putting it into the softmax by 10,000. Now every value, now the stuff that comes out of the softmax will either be 1 if it was the biggest value in that array, or it will be 0. And only sometimes it will be 0.99999 and 0.0001. And then you will have exactly that kind of structure. So and this parameter, in this case, 0. Whatever, 0.1, is called the temperature. And this can actually control somewhat how optimizable certain loss functions are. And in this case, this is just a temperature scaled cross entropy function, which is easy enough. Sometimes this can actually save you and make your model work, but you will always have to try these sort of things. But these things happen, and this is actually a reason why, for example, one work which we'll explore later in self-supervised learning, contrastive learning actually has such a temperature, because otherwise it cannot quite optimize it. All right, the last difficulty fourth difficulty is these cliffs and exploding gradients. So cliffs are, as you can see, just cliffs. So imagine you start off at the left one, for example. First we start off without clipping, because clipping is the solution. You start going down this valley, but then you see then you jump up, and then you end up somewhere else completely. Now with clipping, you just say, okay, the gradient can never be higher than a particular value, namely eta, which is simple enough. So you take the gradient, you divide it by its absolute value, by its length. So now you have a vector which is of length 1, and then you multiply it by the number by the maximum clipping value, and you set that to your new gradient. This is called gradient clipping, and can also make your model sometimes work if it has in particular cases. Sometimes your batch is extremely noisy or extremely difficult, or for whatever reason, sometimes the gradient might explode, and this one will stop it from going too high. Long-term dependencies, you will see, first of all, when you apply recurrent neural networks. So you can think of, for example, applying this matrix W t times, right? So you multiply W and apply some nonlinearity and apply a W and so on and so on. And what you can see, even if it's just a linear layer, it means you're multiplying one with another. So you can do the eigenvalue decomposition, in which case you have the matrix V and the diagonal matrix with the eigenvalues lambda, and then the inverse of V, and you do that to the power of t. And of course, V and the V inverse cancel out, so you can literally just put the to the power of t inside of the diagonal. And now you can think of the eigenvalues. If lambda is bigger than 1, you keep multiplying that with itself, it will eventually explode. And if lambda is smaller than 1, it will go towards 0. And these are called the vanishing and exploding gradient problems, which happen in particular if you have recurrent structures where the same weight is applied multiple times. which makes learning unstable. Another long-term dependency, and I, yeah, you don't have to call it that way, but another time dependency, I would say, is this training trajectory dependency. It's very hard to recover from a bad start. You can try this yourself. You can first train a neural network to, say, give you 0% accuracy on something, and then train it on the normal data set that you wanted to achieve a high accuracy. It's very difficult to get back to a good accuracy after you've had a bad start, essentially. All right, let's talk about advanced optimizers. What can these do? So we know gradient descent. It's this extremely simple formula, right? So what could we possibly innovate from here? Well, we can find a better learning rate or a better gradient, or both. So first of all, let's briefly talk about the learning rate. You've had that very briefly in ML1, but the general rule is that you go from high to low. You do this via learning rate schedules. Typically, what is recommended is, for example, step decay. So you reduce the learning rate, for example, here from 0.1 to 0.01 to 0.001 and so on in some fixed schedule. On the right-hand side, you can see the learning rate being plotted. On the left-hand side, you can see the training loss. And you can see that each time the learning rate is decayed, decay is the same as made smaller. It's not really decaying like exponential here, but each time the learning rate is decayed, you can see that the loss drops by a huge amount. Because suddenly it's not doing these huge steps anymore, jumping from mountain range to mountain range essentially, but now it's having smaller steps and can explore within that range to find the lowest value possible, or highest value if we stay with the mountains. Another learning rate that is very popular nowadays, which is sort of the always works, is the half cosine with warm-up. So you have a linear warm-up schedule, which goes up for a few steps. And then you have a decay which follows the cosine part, the cosine that starts at 1 and then goes down. And this is basically a smooth version of this step decay. And this learning rate warm-up is, you can also skip that part, but it's sometimes quite useful because the neural network components, various components need some warm-up. Similarly for advanced optimizers which keep a memory of the past gradients, which we'll go into in a bit later. But basically this is all you need to know about setting the learning rate. Now we'll talk about the advanced optimizers. So the first two things are will add momentum. Yeah? Yeah? The warm-up is in a way, so for example, for some optimizers, you're trying to estimate some quantities. For example, where has a gradient pointed in the past? And if you right from the bat start having a learning rate of 0.1, you might be going all the way in the wrong direction, and it's hard to recover from a bad direction. That's why you first take sort of timid steps until you know, okay, everything is warmed up, everything is sort of, the estimates will be more or less correct, and then you start doing larger steps. Yeah. For normal, well, there's another component sometimes in neural networks, which is batch norm, which can also need some warm up. So depending on the network, this will still make a difference. Yeah. Yes. Right. No, you keep the batch size the same. Yeah. Because otherwise there also isn't much of an effect, and you wanna keep the batch size constant throughout training. I've sometimes changed it, but not on purpose because I had to switch to a different GPU. You don't want to do that. Any other? Yeah. I would say typically no, because it's hard to do. Like, I mean, so there's other kinds of learning rate schedule, which is called decay at plateau. So it basically monitors how your training loss is looking like. And in this case, it would be quite clear. So it's sort of plateauing, and then it would automatically divide the learning rate by 0.01. But then if you run it the next time, it might drop it 2 epochs later, 5 epochs earlier. So it's somewhat not reproducible. But yeah, if you're in a company and you just want to solve a problem, you can use these sort of drop schedules. And by the way, one good thing about these kind of drop schedules that keep a constant learning rate is, and that might be useful for your thesis or for other projects, is if you decide, if you're trying to explore whether you should drop at 30 or at 50, well, you can always train until 30 and use that same checkpoint for then dropping it immediately afterwards, or for keeping training for another 20 epochs and then dropping it. So yeah, if you care about the environment, maybe use a learning rate decay. All right. Any other questions? And otherwise, just say something as well. Yes? There's a bunch of reasons why you wouldn't. Like, first of all, as I said, keep the GPU maximally occupied. So if you then change the batch size, you wouldn't be using it maximally anymore because you would only go down. Secondly, yeah, there's a bunch of components which matter in terms of batch size. Sometimes, most times, the loss is averaged across the batch size. So you compute the loss for each sample and then you average it by the number of samples. Sometimes it's not. Sometimes it's just summed up, in which case the loss, the whole value would change. And so yeah, these are the main reasons. When you do the validation loop at inference, this is completely different. Like at inference, you're not computing, you're not storing the gradients, you're not computing the backward pass. You can easily use a larger batch size. It doesn't matter. But make sure you're actually in the validation loop. Otherwise, yeah, things get bad. All right, cool. Then let's move on to momentum. For this, let's get some momentum. So momentum. This is the visualization of what we'll be doing. So we're optimizing. We go down the hill. And by the way, this is great. It's in the UK. They have the National Health Service, so everyone is covered. And yeah, whoever picks the cheese first is I think, the winner of that village. But importantly, that piece of cheese, and I don't know why this video is like super long, but this piece of cheese will, if there's even a tiny hill now in this hill, it would go above it and keep going down, right? This is the idea. So even if you get stuck in a local minima, if you have built enough momentum, you can cross that and keep going until you land at the lowest spot, essentially. All right. And for this, we'll first look at exponentially weighted moving averages. So for example, let's suppose you have a sequence of numbers, S, and they are quite noisy. Noisy because, I don't know, we cannot quite measure the original one, and there's some noise process going on, etc. And we wanna denoise this, essentially. And hint, what we'll be looking at instead of these noisy data points, noisy sequences, we'll be looking at noisy gradients. So let's take a look at this. So we'll be using the following formula for computing exponentially weighted averages. So we'll be going from left to right and simply applying this formula where the next sample is given by a linear combination of the previous sample and the current measurement, ST. And it's a convex combination, so you don't have anything that's blowing up. So always, if you just apply it to a constant function, you'll get a constant function, right? And the only thing missing in this formula is you need some sort of starting point. In this case, the starting point here is picked as 0. And then you can literally apply this one. And depending on what kind of beta value you use, you will, for example, if you have a very high beta value, you will always be very close to, is this, yeah, maybe this one is the opposite definition of beta. I'll double check this one. But if we stick with the plot, if you, oh no, it's actually correct. If you have a very low value of beta, for example 0.5, it approximates very closely the sequence S. If you have a very high value of beta, it smoothes over all the differences. And you can see, obviously, this beta of 0.98 is over smoothing it, and the red one is still quite noisy. So you typically want to find a nice balance. And well, as it so happens, in this case, 0.9 is a good balance. And as it so happens, this is also what is the case for gradient descent and for the more advanced optimizers. And actually, this point about V0 being 0 is, of course, a bit bad, because imagine if this time series was starting at 100 instead, having the first estimate be 0 is not very good. And you can actually do the mathematics, and you just simply take whatever you had and divide it by 1 minus beta to the power of t, where t is your number of time steps, and then you end up at the corrected estimates, which doesn't tend towards 0. So you can also see from this formula that if t is, say, 100, at that point, this correction term doesn't have any effect anymore, because you're doing 1 minus what is essentially 0. So you're keeping the normal value. So this bias correction term really just has an effect at the beginning. Now if we simply plug this formula in, for example, for the previous point, so now you can see Vt minus 2. You can see that there's a multiplication of betas happening. And if you do this enough times, you end up at very small values. And that's why it's called exponential weighting, exponential weighted averages, because the decay goes exponentially, because you're keeping values which are smaller than 1, and you multiply them with themselves. All right, so let's do SGD with momentum. What does it look like? So if you look at this usual update formula that we had, WT plus 1 is WT minus, and we used to have eta times GT, so the gradient. Now we are adding a gamma times VT. And VT is simply this momentum now. So V kind of reminds us of velocity. And so now we're simply adding this to the current estimate of the gradient. And so we're basically keeping some momentum from the previous update. We're keeping the velocity, the direction especially, of the previous update, and we're sort of averaging them together, and that's the direction we'll be going instead. And we'll be using this exponential averaging because we want to have some effect from the past, but we want to forget the past as well. So that's kind of the medium that's in between. And if we look at how this is implemented in terms of code, it's the easiest way to write it, right? So you compute the gradient using backprop. We had that the last time. And then you update your weights. In this case, the minus equals means W equals W minus, as you know. You have learning rate times this gradient step. That's SGD. And now SGD plus momentum has this pre-computation, basically. So in this case, W is W minus learning rate times V. And V itself is this linear combination of the original gradient. That's the same as SGD. But we add to this row times previous value of V. And of course, this updates V recursively. And yeah, you can see it as building up velocity and keep going this way. There's this kind of, what you can see here is, for example, gradient descent is the light blue ball. And if you have momentum, that's the violet ball. And these are other optimizers we'll go into the next slides. But you can see this one takes quite long to actually go to a local minimum, even though it's not even the global minimum. In which case here, only Adam, the optimizer we'll be talking about soon in the next few slides, goes actually to the global minimum. All right. So roughly, the analogy is this ball going down a hill with building up momentum. and which also means that and I've been speaking about what this means for ill conditioning. For ill-conditioned problems, they kind of look like this ellipsoid or this very valley-like structure. And since you're blind, you can never just stop here and then go towards the global minimum, but instead you would be zigzagging. But if you now build up momentum, you sort of remember which directions were good, and you can reduce this zigzagging behavior. You can even be a bit smarter than that by something called the Nesterov momentum. So the Nesterov momentum is don't compute the gradient at the current location, but actually take a step first of your previous gradients and compute the loss at that step. So the only thing now is that the gradient dw is not evaluated at wt, but instead at wt minus gamma minus this momentum update. So basically, if this is the normal result that you get with if you apply the gradient and the momentum, now you first apply the momentum and then compute the gradient at this location. So you end up at a slightly different update equation. Yeah. So in a way, you're giving this the algorithm the kind of prescience because it's first looking ahead, and instead of compute the gradient, but actually we're going to go a different direction. So in a way, this is much smarter, and this actually makes RNNs a lot more trainable. And there's some nice theoretical guarantees for this algorithm as well. Right, this is another visualization. It's the same thing. Adaptive step sizes is the next important part. So we've said that learning rate sort of tells us how far we go. And it is one of the most difficult hyperparameters that we need to set, because we cannot do gradient descent on learning rate, right? With what learning rate would you do that? People have tried, by the way. There's some papers which sort of have a neural network which tells how the other neural network needs to be learned, but that's extremely difficult and doesn't really generalize, because then that network also has hyperparameters. So the key innovation that people have done is, let's make this learning rate adaptive. Adaptive not only to where we are in terms of training time, but in terms of adaptive to each parameter itself. So we'll be talking about these three optimizers: Adagrad, RMSprop, and Adam. Adagrad is the following. So the main idea, and it was one of the first, is that we adapt the learning rate for each parameter using the past observations. And we're going to decrease the learning rate fairly quickly, especially when there's when the gradients are large. So the update equation simply looks as follows. R is the squared gradient size. So it tells us how big the gradient was. And then we simply update W by decreasing this step size with this W and simply multiplying it per parameter with the original gradient we had. So in this case, R is a vector of size, the number of weights, which of course introduces additional memory requirements, because now we need to keep track of even more parameters in our memory. Adagrad has advantages. It sort of eliminates, or the idea is that it eliminates the need to tune the learning rate, and generally works a bit better. There's also Ada Delta, which has which adapt these even further, because at the moment, for example, if you see here this learning rate decay, it simply sums over t, right? This is bad. Like, if you will hit zero gradients pretty soon with this crazy approach, or this very aggressive approach, let's call it. So Ada Delta basically makes a fixed window of these, so it doesn't aggressively decay towards zero. RMSprop is another adaptation. It's called root mean squared propagation, and it's basically a modified version of Adagrad, where you use exponentially weighted averages instead to get to the gradients. RMSprop is, by the way, another, well, and you can apply these gradients. RMSprop firstly looks like this. So you can see this Adagrad equation, VT here. But instead of RT being defined as an eta grad, you have this exponentially weighted average. And again, you have this sort of decay hyperparameter. So now you have this, you not only have this epsilon, which prevents it from like exploding, because once RT hits 0, dividing by 0 will throw you an error. That's why you have a small value epsilon, which never has any impact as long as the square root of RT stays somewhat positive, or stays positive essentially. But now you have this additional hyperparameter of 0.9. Right. It has these properties that it sort of tames the noisy surface and can prevents it from getting stuck. One part about RMS prop that's good to know is it's actually it was never published. So it's one thing that is an innovation in deep learning, and everyone pretty much knows about it, but it was never in a paper or anything. It's just in a lecture from Geoffrey Hinton. And so if you cite that algorithm, you typically cite a lecture, which is quite fun. But moving on to the most important, and I think most cited machine learning paper that exists, which is ADAM. It stands for Adaptive Moment Estimation, and it's sort of a combination between RMS prop and momentum. Again, it computes an adaptive learning rate for each parameter, which again, each parameter you should remember that requires high memory, and keeps exponentially decaying averages. Generally, it's the best place to start, and because it's not that hyperparameter dependent, and it's one of the most popular learning algorithms, and is the only one which works for these transformer architectures that we'll be talking in lecture 7. The algorithm is given as follows. Again, you recognize the similar bits with RMS prop. You also recognize these beta to the power of t's, which are bias correction terms, except now you have two betas. One is at 0.9 and one is at 0.999. You typically do not change these, which makes it a lot easier for a user to optimize this. But you need to keep in mind that it still requires an initial learning rate. So you still need to set this one, but it doesn't really matter all that much. In SGD, it will matter a lot whether you set it to 0.1 or 0.3. In Adam, not so much. You can use 1, you can use 0.1. Sometimes it doesn't matter because of this adaptive step behavior. Here's a visual overview where you can clearly see that Adam is sort of pretty much nails it versus gradient descent here. You have full data set gradient descent. It sort of slashes around. This is a sort of cheat sheet or overview. Typically, SGD plus momentum works best for convolutional neural networks, at least. But Adam is typically the preferred choice because it's much easier, less finicky. But sometimes if you really want to get the highest performance, again, at least with convolutional neural networks, you want to use SGD because Adam doesn't give you the best values. Again, with weight decay, that's the one that's standard for transformers. And this is a really surprising thing for me. But when I found this out, even for Adam, you actually do this learning rate drops and this this cosine learning rate decay, which is very strange. And I don't think I've seen a paper yet that explains why we need this, but actually it does help a lot. It doesn't help, it's not as crucial as if you were doing it with SGD, because in SGD you have the fixed steps, but it still helps even if you do something with Adam. Yes? Because Adam already adapts this learning rate step size. So even every parameter already has its own learning rate, basically. So you're adapting it twice, yeah. And you're adapting it in a sort of ad hoc manner now, which I think that's probably, yeah, it's sort of, you're imposing it a structure. Okay, you've done enough global search, now do some more local search, now some even more local search. But yeah, yes? Yeah, so typically you have an object called an optimizer in Torch, that's Adam, and then you can say something like, if epoch equals 30, then take your optimizer, divide the learning rate by 10. If epoch 60, take it, and so on. they're not learning rates. They're not called learning rates. They're like momenta and so on. And you don't override these. No, they stay the same basically. You're simply saying, okay, all these directions of previous gradients, we keep them in memory even at epoch 30 to 31. We keep them the same. But now we're simply this last step that we do in the Adam algorithm of multiplying by eta. Now simply this number becomes slightly lower. That's all we do. Yes.
So for Adam, there are these three hyperparameters that are sort of, there are three values of these hyperparameters that are default, like the 0 0.9, 0
Mm-hmm.
0.999,
And epsilon, yeah.
it seems a bit counterintuitive to me, or it makes me a bit weird that these should be good values regardless of the task and
Yeah.
task landscape.
Yeah, I think in part the algorithm was designed basically such that these generalize to all kinds of tasks. So that was almost literally their goal. Um, at at some point, you also reach the point where, like, for example, you might come up with a new architecture, but if you don't have the right optimization algorithm, that architecture might never get published, right? So maybe there's also a chicken and egg problem that the architectures we have, they are the architectures that can be trained with SGD or Adam. So yeah, that might explain partly why it's not too surprising that Adam works on a bunch of things. But as I said, you can always find a problem where Adam doesn't work, just like you can always find a problem where SGD doesn't work. All right, we'll briefly dive into second order methods. So as I said, like if we could know a bit more about where we are, if we have more than just a measuring stick, we could do a lot better optimizations. And typically in the 1D case, this is called Newton's method. And the basic idea is that you do a Taylor series expansion at a given point, and at this given point, where at a critical point, you want to solve it for a critical point, where critical point here is defined as the first derivative being 0, then you get this sort of update rule, which obviously needs to depend on the Hessian, but this will give you the exact solution for a quadratic function. And for non-quadratic functions, you can apply this iteratively. The equation, well, okay, the equation generally is quite tricky to use in the regular case because it depends on the Hessian, but quasi-Newton algorithms use the fact that we go alongside, we sort of capture gradient signals as we go along in this weight landscape, and we can compute some approximations to the Hessian. And these are what are called quasi-Newton methods. One of these is the most popular, which is BFGS. It approximates the Hessian matrix using low rank updates that it can get. From the previous gradients. They are better in terms of optimization, have some guarantees, and use second order information, but they're somewhat rarely used. This one just shows you another set of balls running around, and you can play around with that one. Let's move on to the third part of the mini-series. Step 1 and 2 were understand fundamentals, read papers. Step 3 is reproducing results. Again, deep learning is engineering science. So start reproducing results and playing around. If you like a paper, try to implement it from scratch. Compare it against, after that, ideally compare it against the open source version of the authors, or maybe someone else has reproduced it. And then you can find out, okay, what did you misunderstand? What is being done differently? Maybe you simply implemented it from the paper, and in their version, they actually included some tiny bits which make it work. Or maybe that's the stuff that actually makes it work. It shouldn't be the case, but sometimes these tricks and hacks are extremely important. And it's very important to get familiar with these sort of things. All right, quiz time. You start with stochastic gradient descent. Or for that matter, Adam. What of these options will not work? If all the weights are initialized to zeros, if we initialize all the weights to zeros, but the bias is to 1. So in this case, I'm talking about this being weights and these being biases, right? or if all of the weights are set to a fixed set of random numbers, let's say random numbers from 0 to 200, or option number 4, setting all the weights to 42. Which one won't work? All right, 3, 2, 1. 1, 1, 1, 1, 1, 1, 1, 1, 2, 2, 3, 2, 3, and jumping around. Right, okay. First one, you're right, that won't work because all the activations will be 0. So that's not great. Number 2 will work indeed because this one being random, it will at least give you non-zero outputs. All the weights set to a fixed set of random numbers, it will work. Not as great as if you initialize it in some more systematic ways. Setting all the weights to 42, you're right. 43 would work though. No, just kidding. This is what happens actually if you set all the weights to one value. In the first, here we're plotting at the top layer, we're plotting the gradient, and then the bottom value, we're plotting the activations. As you can see, if all the values, the weights are the same, the gradients will all be the same. So they will all go the same step direction, so you will never learn something particularly meaningful. And you will actually see this in the tutorial of next week. But let's talk a bit more seriously about initialization, namely about initialization of the weights. So you have your neural network, you've set however many layers of an MLP. Now you want to start with some weights. You don't want to start with 0 because then you're not getting any gradients, so you cannot really do gradient descent. And you want to prevent the activations to be exploding or vanishing, right? You want some gradient signals. So we want to initialize the weights correctly. And if we use 0 initialization, well, we have the sort of benefit that it sort of gives you the same output as a linear model. So that's nice. And if we set the biases, well, setting the biases to 0 will not create any problems, but it's not really learning anything. Now, random initialization, that's what we're going to talk about, and that's what everyone is using. This has the property that it breaks the symmetry and it prevents neurons from learning the same features, right? So every gradient, every random number is slightly different, so every gradient will be slightly different. So random is a good choice, but how should we initialize it? The idea is to preserve the variance of the activations, doing the forward and backward pass. So we want the input and output variance to be similar because of the modularity. So we don't want stuff that's to be, for example, very different at the last layer, but if we backprop all the way to the first layer, they're all mushed together because then we're not getting any meaningful gradients. Yeah, that's what we said. And this initialization now actually isn't, you cannot simply pick any random distribution, you cannot pick random uniform between 0 and your favorite number, but it will depend on what kind of nonlinearities or activation functions you have in your network and what kind of normalizations you're doing. For example, if you initialize weights in every layer with the same constant variance, which seems like a normal thing to do, every weights layers are initialized between 0 and 1 Gaussian. So the first layer, yeah, the gradients will also be between 0 and 1. But if you go all the way to layer 8, by that point the activations will be Gaussian times Gaussian times Gaussian and all these nonlinearities as well. You'll end up at values which are heavily truncated and only range between 0.01 and negative 0.01. If you initialize the layers now, okay, you're saying, okay, so the values go lower the further deeper down you go to the network. So let's increase the variance. Well, that also won't work, not at least that simply. So you start off with minus 10 and 10, and you end up now at 50 and minus 50. And if you're not careful, this will easily explode, and you will have gradients which are minus 1 million, and then you run into overflow, and then it also won't work. So you need to be a bit systematic about this. And it's not particularly difficult, but it requires some mathematics. So let's take a look at such an equation. So first of all, this is a formula from statistics. You know, if you have two independent variables, the variance is given as follows. Yeah, as this one. Now let's say our activation is W times X. So the variance of this one is simply we plug in this formula, which means it's D times variance of that. We plug it in. And since both are zero-centered, let's say xi and wi are unit Gaussians, so we get the expectations at least to be zero. So these cancel out. So you have the variance of each wi times xi is simply the variance of xi times the variance of wi, which we know. And so we can simply, and in the above formula here we have the sum. So this is simply d times the variance of each. Now, what can we do with this? Since we want the same input and output variance, we can now write it as follows. So if the variance of A is now D times variance Xi and variance of Wi. And so we simply need to get rid of this D and then we keep the same variance, right? So if Wi is simply divided by D, then the output would have the same variance as the input. So we draw the weights simply from this normal distribution and then divided by divided by D. And D in this case, as we saw, it's a summation. D is simply the number of input variables to the layer. Now with ReLU nonlinearity, you have to be somewhat a bit more careful because ReLUs return zero half of the time, and they're not symmetric around the axis, right? So if you think about putting a Gaussian on this one, you will get slightly different results. And you can do the mathematics again, and you basically find out that, oh, because it's zeroing half of the time, you actually need to multiply it by 2. And you can actually argue this in a more systematic manner. And this is what has been done in this paper below. And this is called the Keiming initialization after the first author, Keiming Hay. There's more complicated initializations, but these all depend on what kind of activation functions you're using. For example, the Xavier initialization is for tan-h nonlinearities and gives you this formula. Again, the idea is always the same. You want to keep the same variance for input and output of a module. All right. Now, that being said about the random initializations, there's actually some really interesting results within randomly initialized neural network. And so I find this paper quite interesting called What's Hidden in a Randomly Weighted Neural Network. And what they do is the following. They find an algorithm which can do the following. They find that hidden in a randomly initialized wide ResNet 50, which is just an architecture, they find a subnetwork which has completely random weights that matches the performance of a ResNet 34 trained on ImageNet. Right? So they have a network which simply has random weighted connections, but you take this network and then you apply it on a data set called ImageNet, and it matches the performance of a network that was actually trained, where the weights were actually trained. So this, yeah? So the random weights are as initialized, but you need the data set to find the right subnetwork. So you have this big wide ResNet, for example, the one in the middle, and then you find a subnetwork tau dash within this network. And everything else you make zero, basically all the other connections you make zero. And then if you apply this subnetwork, you get pretty decent performance. The wide ResNet, none of these weights are trained. What you train is the mask, basically, this mask of what you zero out. Yeah? You can do the mathematics of how impossible that would be. And I don't mean this in a bad way. Like that would be the way to do it, but and that's why they wrote a paper, because you need to think about it. How can you find such a mask, basically? And they do it in an extremely smart way, which uses backprops. So I would recommend reading this one. And the reason why this works, and this is not the first paper that tells us that random matrices or random values are actually pretty good. So for example, firstly, random matrices, you need to remember they're essentially full rank. So they don't lose any information, which means if you apply, for example, you know PCA, well, you know you can, instead of using PCA, you can also just use a random matrix which projects it into 2 dimensions, and you get similar results because the distances are kept. And actually, as a side note, I have one master student actually working on this topic to generalize this. But all this is to say, like, there's some unexpected results in neural network research and deep learning, and they're quite fun to look into. Right. These are reading materials, and yeah, now we have a break for 15 minutes, and then, as I mentioned on Canvas, Philip Lippe is sick today. So the tutorial, we'll just recommend watching the YouTube video online, and you can ask questions on Piazza. And instead, in 15 minutes, we'll be having the regular TA sessions with the TAs from the first assignment present. So see you then.